This video is about the concept of intersection of sets. Um, Let us begin with the intuition behind the idea of intersection of sets, and then we're going to formalize it. So in other words, let us first talk about intersection of two collections, or maybe more than two. So let's say we've got three collections, in fact. Um, a yellow collection, a green collection, um, but now the area in the overlap of the two regions. Let me actually use white color for that, and the red collection. Um, well, perhaps I'm going to use orange for the overlap of red and yellow, and blue for the overlap for that overlap there, and brown for this overlap here. Do I have brown color? Let me find brown color. Um, okay, I'm going to look for it in here. There we are. This appears to be brown. Great. We've got brown, and let me use black or perhaps gray for the overlap of all three areas. Okay, so um, this picture is very abstract picture. It has colors and all of that. It's not yet a mathematical idea of intersection. For that, we need to have actual objects in each of these regions. And then, when we do, and there can be multiple of them, intersection refers to taking um, objects that are common to two regions. So now say each of these regions were sets. Let's say this is set A, and let's say this one is set C, and this one is set B. Then the intersection of sets A and B would refer to this collection here, which might or might not be a set, but in fact, by restricted comprehension, it can be seen to be a set as well. It's part of A, for example, and restricted comprehension says that a part of another set that is identifiable by a formula, that's determined by a formula, will be a set as well. So that's the idea of intersection. It's to take a collection that is on the overlap of the two collections, and then that collection, if the two, at least one of them were sets, then that collection will also be a set. But now we want to define this in full generality, where we don't necessarily have three sets, but arbitrary number of those. So what we do now is we say, okay, let's have a whole collection of sets. And in this case, in this example, it's three of them, but there could have been more of them than just three. And then we're going to talk about the intersection of the entire collection. So if this collection, but it must form a set, you see. Otherwise, we might run into paradoxes similar to Russell's paradox. So we actually want to be able to intersect sets when the sets we're intersecting, the collection of those together forms itself a set. And so if this set here, in fact, let me change the notation. Let me actually call this one not ABC, but XYZ. There we go. And let me call this one A. And so when A is a set in a universe, we define its intersection to be a certain set. Now A must be non-empty set. We will see in a moment why we want A not to be empty set. So when A is a non-empty set, we define its intersection to be the set of all those x's which satisfy the following formula. Out of lack of space, I'm going to put the formula in 2 lines. So the formula says for every A, if A is in A, then, so here we're referring to small a and capital A respectively. So if small a is in capital A, then x must be an element of small a. Let's look into the meaning of this formula. So let us see which x's will satisfy that formula in this diagram. So let's begin by picking, for example, let's pick that x there. For example, let's pick this x here. Does this x satisfy the given formula? Well, the formula says for every a something should happen. So I have to now start taking arbitrary a and check across all the a's that this thing really happens, the thing that's written here. However, I know that false always implies anything. So if a small a is not an element of capital A, then this thing automatically will hold true. So that allows me to limit my case study for those small a's which are actually elements of capital A. And then I want to check that all such a's will have the property that x will be an element of that a. So let's begin. Well, there are 3 elements that capital A has, x, y, and z. So let's begin by taking a to be x. And we see that it is an element of A indeed, but x, small x, is not an element of that A. Small x here is not an element of capital X. It falls outside this region. So already for A being capital X, the formula fails. Therefore, this x does not belong to the intersection, right? So this should kind of be an indication to when for which x's the formula will hold. So basically the formula will hold for all the x's that are inside, that are elements of all the elements of A. So these are exactly these ones, right? Exactly these ones. The formula will hold exactly for these x's and no other than these x's. Because you see, by picking small a to be x, y, or z, we will be forcing that x to be in all of these sets, right? Because they have to be in all of these small a's that are elements of capital A. And so we see that the formula then determines a set that matches with the picture with our intention of defining the intersection of sets. So this is how the intersection is defined. Now, there are a few questions to be asked here. For example, how do we know this is actually a set? And that we already explained earlier. Because of restricted comprehension. So the same set can now be rewritten. It can be rewritten like this. I'm going to leave the formula the same, but I'm going to say in the front, I'm going to say, let's pick those x's from, and I'm going to choose a specific member of capital A, let's say capital X, from X satisfying that same formula. So here we've got a copy of the same formula. Now this way I haven't actually changed the collection because you see every X falling in here will automatically fall in X because it's an element of A. So because that region is part of the region of X. So everything in here will automatically be in there. Because being in here means validity of the formula plus the fact that it must be in X, and anything that validates the formula is automatically in X. On the other hand, if something is in here, it means it validates the formula plus it's an element of X. But then, of course, it validates the formula, so it's automatically also then in there. So these two collections are actually the same collection. But now this way of writing it down allows me to apply the restricted comprehension to conclude that it's a set, because by the restricted comprehension, since X is a set, and since it's a collection defined by a formula, by selecting elements from X, satisfying that formula, by the axiom of restricted comprehension, this must be a set also. And this set is exactly the set we're looking for here. So this is how we can confirm that the intersection of A is actually a set. But this argument works based on the fact that we can select a set X from A. We needed it here, right? So A has to have an element. And that's why we wanted A not to be empty. But now, interestingly, if A is empty, right? So imagine A is now empty set. Then which X's will satisfy the formula? Well, if A is empty, then no A will be element of A. So the implication will hold automatically for every A. So for every A, this will always be true, right? This formula is always true then for every X, right? So if A is empty, the intersection of A is going to give the collection of all possible sets. And the collection of all possible sets might not be a set after all. And so that's why we don't want A to be empty set, because we actually want to have the intersection of A to be a set also, and when A is empty, it is not. So the intersection of A is only defined for a non-empty set. In that case, the intersection of A itself is a set, and that's not a separate axiom that follows from the axiom of restricted comprehension. In the case when the set A consists of only two elements, so before we had it consisting of three elements, and now let's consider another example consisting of just two elements. So let's say we call it B. So let's say B consists of just X and Y as its elements. Then the intersection of B also has another way of representation. The notation for that is this. So we take the symbol and now we put it in between those two sets. So by definition, this means the same as that, for B being the set consisting of those two elements. And then we can manipulate with this expression, with this symbol, as if it was an operation on objects, and it is an operation on sets, right? So for example, we could form expressions like this, and that will turn out to be in fact the same as the intersection of the set of X, Y, Z. And one can go ahead now and establish various algebraic properties of the intersection of operation. Sorry, it's the other way around. The operation of intersection. Great. So this is a video on intersection of sets, and just to emphasize, the concept of intersection is defined for a single set, because the idea is that we are intersecting the elements of that set, but it's also defined for two separate sets. And the link with the previous definition is that for two separate sets, when we intersect two sets, what we mean is that we are intersecting the elements of the set consisting of those two sets as its unique element.